Here is a scenario. Your team runs the full testing suite. Everything passes. You deploy to production and the whole thing breaks. Now here's the uncomfortable question. Did your testing fail or did your thinking fail? Because passing tests doesn't mean your system works. And in this video, I will show you how strong engineering teams actually build confidence in their software by testing what actually matters. A programmer might ask, did we test it? Which is a simple yes no question. But true software developers, they ask a much deeper question. How sure are we that this system will behave as expected? This isn't about a checkbox anymore. It's about the degree of confidence you have in your work. And that's because hoping it works is not a strategy. Strong engineering teams understand this. They understand that testing isn't something you do after you're done coding. It's an integral part of the process. And it's focused on just one thing, gathering concrete evidence that your system does exactly what you claim it does. So, where do you even start? The first pillar of any strong testing strategy is to focus your effort where it matters most. It's about being strategic, about really assessing risk, impact, and uncertainty. You have to start asking the right questions. In what ways can the system fail? What risks are we trying to reduce? What assumptions must be validated? Where would a bug cause the most amount of damage? Did you notice how these questions shift your focus from design or code to actual real world consequences? That is strategic thinking. Here is an example. Imagine you have built a billing system. You have got 500 unit tests and every single one passes. But that number only means something if those tests reflect real world behavior. What happens if payment processing is delayed? What happens if a user upgrades their plan right in the middle of a billing cycle? Or the tax rule changes overnight? Or a payment retry accidentally happens twice? Now you are not testing code anymore. You are testing reality. And this is the shift. Testing isn't about proving your code works. It is about exposing how it can fail. And those failures, they don't always show up neatly inside your test cases. Which brings us to our next pillar, testing with real data. Your test cases are only as useful as the data behind them. Artificial data creates artificial confidence. Ask yourself, does the test data reflect real world usage patterns? Are we validating behavior under messy and imperfect inputs? Consider a search function that is tested only with short, well formatted queries. It will soon discover that users behave differently in production. They copy paste long paragraphs, enter special characters, submit incomplete or malformed input, perform thousands of searches simultaneously during peak hours. Your testing must reflect that reality. And real world data is inconsistent, noisy, and unpredictable. That brings us to testing under stress. It is important to know how the system performs under peak load and beyond it. What happens when dependencies slow down or fail? When a database becomes unavailable? When the network slows down? When disk becomes full? When the system runs out of CPU or memory? Do we even know when and how our software degrades? And most importantly, are we able to simulate such failures? Imagine an e-commerce website during a huge sale. It's the holiday season. The traffic spikes and a key service, your payment processor, is overloaded. A fragile system will collapse completely. Your checkout page will crash and nobody will be able to buy anything. A total disaster. But a resilient system is designed for this. It degrades gracefully, disabling a few features, but keeping the core shopping experience alive. Because the engineers understand that it's not about preventing failure altogether. Because, let's face it, that's impossible. It's about designing systems that can handle a failure without a complete outage. The goal is to have known breaking points and not surprising ones that will catch you off guard. And the right kind of testing is how you find those breaking points. Now we get to maybe the most important point of all, designing for failure. Ultimate confidence doesn't come from believing that your system will never fail. It comes from knowing that when it inevitably does fail, you have the tools to understand why and fix it fast. It's all about diagnosability. Think about this all too common scenario. An order fails. You check the logs and they are completely useless. Just generic error messages. There is no way to trace the request across different services. So what happens next? A team of engineers spends days not analyzing but guessing. With a system designed for diagnosability, every request has a correlation ID. State transitions are logged correctly. The logs are clear and the problems are traceable. Retry attempts are well recorded. What was a 2-day mystery, it now becomes a 10-minute process for a single engineer. That is the power of designing for failure. So now you have tested for risk, for stress, and you have embraced diagnosability. But you are still not done because building confidence is not a one time project. It's an ongoing discipline that you have to maintain with every single release you push. This means having automated regression tests to make sure new changes don't break old functionality. It means actively monitoring production to see if the system's behavior actually matches what you expect. And crucially, it means building a culture where failures are treated as learning opportunities and not reasons to point fingers and assign blame. Ultimately, this is the core idea we have been building towards this whole time. True professional confidence isn't about the naive belief that your system is perfect. It's about having the mature ability to understand failures quickly and act with total clarity when they do happen. So I will leave you with the same question we started with, but maybe now with a totally new perspective. For the system you are working on right now, don't just ask if you have tested it. Ask yourself, based on the evidence you have gathered, how sure are you?